Most people walk past rocks like these and without a second glance. Rough, broken, completely ordinary. But what if these ugly stones were hiding something far more valuable? Because the truth is, gold doesn't always shine. Sometimes it hides. Locked inside rock, carried through rivers, shaped by forces deep beneath the earth. And unless you know exactly what to look for, you'll never even realize it was there. In this video, we're uncovering the full journey from hidden gold inside stone to the geological forces that create it, to the exact places it gathers, and the clues most people ignore. And by the end, you won't just see rocks the same way again. You'll start seeing what others miss. They look ordinary, rough, ugly. The kind of rocks most people would kick aside without a second glance. But what if I told you that inside these dull and lifeless stones could be one of the Earth's purest treasures? Gold? It sounds unbelievable, doesn't it? Yet for centuries, nature has hidden gold in the most unexpected forms. Not in glittering nuggets lying openly in streams, but deep inside rocks that seem completely worthless. Today, we're not just talking theory. We're going to uncover a natural process, one that doesn't require chemicals, mercury, or fancy machines, but instead uses what nature itself provides: fire, water, and patience. This is how you find gold in rocks that everyone else ignores. This is where it begins, with the search. When you start looking for gold in nature, you must unlearn everything you think you know about beauty. Gold doesn't always hide inside beautiful, shining quartz crystals. In fact, many of the richest deposits are concealed within rocks that appear dull, rust-colored, even broken. You see, the Earth's crust tells stories, and those stories are written in color, texture, and formation. Look for rocks with iron staining, those deep red and brown patches caused by oxidized minerals. They might look like rusted scrap metal, but that's exactly what you want. Iron oxides and sulfides often indicate hydrothermal activity, the same process that once brought molten gold up from deep underground veins. If you see tiny metallic sparkles, but they don't look like glittering gold, don't walk away yet. Many of these flecks are pyrite or arsenopyrite, minerals that form alongside gold. These are the clues, the whispers from the earth that tell you gold might be near. Once you collect a few candidate rocks, ironstones, quartz with rusty veins, or dense black and brown stones with weight, the next step begins. It's time to reveal what's hidden inside. For thousands of years before modern refineries and chemicals, prospectors used fire to separate the worthless from the valuable. Fire, in its purest form, doesn't destroy gold. It reveals it. When you heat a rock, something remarkable happens: thermal expansion. Each mineral inside that rock expands at a slightly different rate when exposed to high temperatures. That means under the heat, the internal bonds start to weaken. Tiny fractures form. The rock begins to loosen its grip on whatever's trapped within, including gold. Now, this process isn't about melting gold. It's about breaking the prison that holds it. You don't need industrial furnaces. Even a simple controlled fire, fueled by charcoal or dry wood, can create enough heat to fracture softer mineral bonds. The key is patience. Let the fire do its work slowly. Rushing it might cause the rock to burst unevenly, wasting both material and effort. But when the heat has done its job, you'll notice a subtle change. The surface dulls, the rock looks tired, as if it's about to tell its secret. And that's when you introduce nature's second element. When the red-hot rock meets cold water, nature performs one of its most powerful transformations. The sudden temperature change causes thermal shock. The rock cracks open from within. You'll hear it, small pops and cracks as the water penetrates the fractures, widening them. This isn't just a satisfying sound. It's the sound of progress. The rock is breaking apart, layer by layer, exposing its inner matrix where gold might be trapped. Now, as you lift those cooled rocks, you'll notice they feel lighter. Some have split cleanly, others crumble between your fingers. That's when the real revealing begins. What was once solid stone now breaks easily. Inside, you'll notice veins, metallic threads, or dull patches, all of which could indicate gold. Crushing doesn't mean pulverizing everything into dust. It's a methodical process. The goal is to reduce the rock into smaller pieces until you can examine what lies within, and sometimes you'll see it. That faint, buttery glimmer that refuses to tarnish, no matter how much you rub it. That's not pyrite, that's gold. When gold forms in nature, it bonds with quartz, sulfides, or iron-rich minerals. The heat and cooling process frees it from its original bonds. What you're doing now, crushing, is simply helping the Earth finish what it started millions of years ago. Each tap, each crack, brings you closer to what prospectors once called the mother's gift. But there's one more step, the separation, and it doesn't need any chemicals, just clever observation and patience. Gold is one of the heaviest elements found in nature. That simple truth can be your biggest advantage. Take your crushed material and place it in a shallow pan or a wide container filled with clean water. Gently swirl it. Don't rush. The lighter materials, sand, dust, and rock, will float or move to the top. But the heavier particles, including any gold, will stay stubbornly at the bottom. This natural principle of gravity separation is the foundation of panning. It's how ancient civilizations discovered gold long before chemistry existed. As you tilt the container slightly and let water wash away the light debris, what remains might surprise you. Tiny golden fragments, specks, or even flakes glinting in the sunlight. Each one tells a story older than humanity itself. For most people, rocks are lifeless. But for those who understand the Earth's language, every fracture, color, and shimmer is a clue. You've just transformed what appeared to be worthless stone into something extraordinary, using nothing but natural forces, fire, water, and gravity. The process might seem simple, but it's one of the oldest forms of natural gold liberation on record. It's proof that you don't always need chemicals or machines to work with nature. Sometimes all you need is understanding. And here's the secret most overlook. The real value isn't just in the gold you find, but in learning how nature conceals and reveals its riches. That knowledge is what separates a casual explorer from a true prospector. You didn't just extract gold today, you uncovered a truth that's been buried for centuries.
Most people think gold is inside rocks. That's not entirely wrong, but it's also not accurate. Because gold doesn't originate in the rock you're holding. It arrives there, carried by fluids moving deep beneath the Earth's surface. Superheated, mineral-rich solutions traveling through fractures you'll never see. Now think about that. Gold isn't placed, it's transported. And when those fluids begin to cool, something changes. The rock doesn't create gold. It traps it. But once gold is trapped, it becomes a problem. Not because it's rare, but because it's locked. And locked gold has no value until it is released. Here's the part most people completely misunderstand. Gold in rock is almost never sitting there as visible nuggets. It's not waiting to be picked out. It's embedded, threaded through fractures, dispersed in microscopic particles, bonded within the structure of the host rock itself. So when someone picks up a rock and looks for gold, they're already too late, because visible gold is the exception. Locked gold is the rule, which leads to the only question that matters. How do you get gold out of rock that doesn't want to give it up? The answer is simple, but not easy. You break the rock, not casually, not superficially. You destroy its structure completely, because gold is not released by exposure. It is released by reduction. The rock must go from solid to fragments to powder. Think about what that actually means. A rock that looks solid and stable is acting like a container. Every fracture inside it is sealed. Every microscopic space is closed. Gold is there, but inaccessible. The moment you break that rock, you don't release gold immediately. You only create access to smaller locked sections, and those sections still hold gold. So the process continues. Break it again, and again, and again, until the structure no longer exists. At that point, something important happens. You're no longer dealing with rock. You're dealing with particles, and particles behave differently. Now gold starts to reveal its advantage, not visually, but physically. Gold is dense, much denser than the material that surrounds it. So when the rock is reduced to fine particles, gold stops behaving like everything else. This is the moment of true extraction, not when the rock is broken, but when the material is separated. Because crushing alone does not extract gold. It only prepares it. Separation is what completes it. Now imagine two materials mixed together, pulverized rock and tiny particles of gold. They don't look different at first, but once movement is introduced, everything changes. When water is added or motion begins, lighter material lifts, heavier material settles, and gold, being one of the heaviest components, moves downward. This is why crushing must be precise, too coarse, and gold remains locked inside fragments, too fine, and you risk losing it if you don't control the process. Professionals understand this balance. They don't just break rock randomly. They reduce it to a size where gold can separate efficiently. Now, here's where the system becomes more strategic. Not all rocks are worth crushing, because crushing is effort, and effort must be directed. The key is not breaking every rock, but identifying which rocks are most likely to contain trapped gold. And this is where structure becomes important again. Not for trapping, but for targeting. Rocks that have experienced pressure, fracturing, and fluid movement are far more likely to contain gold. Because those are the rocks that were part of the transport system. But here's the mistake most people make. They only look for visible signs, shiny surfaces, obvious veins, clear indicators. In reality, the best gold-bearing rocks often look worse. Dull, broken, iron-stained, structurally disturbed. Because those features are not flaws. They are evidence. Evidence that fluids moved through the rock. Evidence that conditions changed. Evidence that trapping occurred. And if trapping occurred, crushing becomes meaningful. Now imagine holding two rocks. One is clean, solid, visually appealing. The other is fractured, stained, irregular. Most people choose the first. Professionals choose the second. Because they are not choosing appearance, they are choosing probability. Now, let's go deeper into the crushing process itself, because this is where extraction either succeeds or fails completely. Initial breaking reduces the rock into manageable pieces, but that stage doesn't release most of the gold. It only reduces size. Secondary crushing targets internal structures. This is where fractures are opened. Hidden zones are exposed. But even here, gold is still partially locked. The final stage is critical. Pulverization, reducing material to fine consistency, where individual mineral grains separate from each other. At this point, gold is no longer attached. It is free. And once it is free, it behaves according to physics, not structure. This is the transition point most people never reach. They stop too early. They break rock once or twice, don't see gold, and assume it isn't there. But the absence of visible gold at early stages means nothing, because extraction has not yet occurred. Now consider efficiency again. Every stage of crushing increases the probability of release, but it also increases the need for control. Because once gold is free, it can be lost just as easily as it can be recovered. This is why professionals combine crushing with controlled separation. They don't just create particles, they manage them. And here's the final shift in understanding. Gold is not difficult to extract because it is rare. It is difficult to extract because it is hidden inside structure. Remove the structure, and the problem disappears. So the real skill is not finding gold. It's deciding what is worth breaking. Because once you choose the right rock, the rest becomes a process. Break, reduce, separate. And if the system is followed correctly, gold does not stay hidden. Now the process shifts from theory to execution. Because once you decide a rock is worth breaking, everything depends on how you break it. Start with primary reduction. Most people hit the rock randomly, trying to break it open in one strike. But that creates uneven fragments. Some pieces stay too large, still locking gold inside. Others become too fine before you can control them. So the goal is not force, it's controlled breakdown. Reduce the rock into consistent pieces, small enough to expose structure, but not so fine that you lose control. Then comes secondary crushing. Now each fragment is reduced further. This is where gold begins to transition from locked to potentially free. But balance matters. Too coarse, gold stays trapped. Too fine, too early, you risk losing it later. So the process is staged. Reduce, check. Reduce again. Then comes the turning point, liberation. This is when gold is no longer attached to the host rock. And from this moment, you're no longer breaking rock. You are managing particles. Now comes the critical phase, separation. Add water, not aggressively, but with control. Movement begins to sort materials. Lighter particles lift and wash away. Heavier ones settle. And gold, because of its density, moves downward. At this stage, gold may not be obvious, because it remains mixed with heavy materials like black sand. So the goal is not to see gold immediately. The goal is to remove everything else. This is where most beginners fail. They search for gold too early, instead of refining the material step by step. Through repeated controlled washing, the concentration increases, and eventually, gold becomes visible. Now the biggest risk, loss. Once gold is free, it can be lost easily, especially fine gold. It doesn't behave like large pieces. It can move with water if the process is too fast, so control becomes everything. Slow movement, balanced water flow, consistent handling. Now understand this clearly. Crushing does not extract gold, it only prepares it. Separation is what completes the process, and both stages must work together. Now step back. Gold is trapped inside rock. Crushing removes the structure. Separation isolates the gold. Control prevents loss. Each step is necessary. Miss one, and the system fails. And that's the difference most people never realize. Gold isn't hard to extract because it's rare. It's hard because it's hidden inside structure. Remove the structure correctly, and gold doesn't stay hidden. Because at that point, you're not guessing anymore. You're following a process. And if gold is there, it will show itself.
If gemstones exist in an area, the landscape almost always leaves clues before a single crystal is found. Prospectors rarely begin by searching for gemstones themselves. Instead, they search for the geological systems that create them. When the right conditions appear in the rock, gemstones become possible. When those conditions are absent, valuable crystals almost never occur, no matter how long someone searches the surface. This is why experienced collectors often spend more time studying rock formations, river structures, and mineral patterns than examining individual stones. The environment reveals where gemstone formation could have happened, long before erosion exposes the crystals. Across regions of the United States, the United Kingdom, and Canada, many gemstone discoveries began with observations like these: a fracture pattern in the rock, an unusual mineral concentration in river gravel, a weathered outcrop that suggested deeper geological activity. Each sign represents evidence of processes that occurred underground long before the present landscape formed. One of the most recognizable geological indicators appears in the form of mineral veins. When the Earth's crust experiences pressure, fractures develop in solid rock. These fractures become pathways for hot groundwater, carrying dissolved minerals. As the fluid cools within the cracks, minerals begin to crystallize and slowly fill the empty space. Quartz is one of the most common minerals formed through this process. In the field, quartz veins appear as pale bands or irregular streaks cutting across darker rock. Sometimes they emerge as thick ridges that resist erosion, standing slightly above the surrounding terrain. In other cases, they break apart into fragments scattered along hillsides or stream beds. Although quartz itself is extremely common, the systems that created these veins often transported many other dissolved elements at the same time. Under the right chemical conditions, minerals such as tourmaline, garnet, and occasionally sapphire may form in association with these hydrothermal environments. For that reason, quartz veins frequently attract the attention of prospectors studying potential gemstone terrain. However, the presence of quartz alone is not enough. The surrounding rock structure must also support the conditions required for crystal formation. Certain metamorphic rocks provide those conditions particularly well. Schist and gneiss form when existing rock is subjected to extreme heat and pressure deep within the Earth's crust. During this transformation, minerals reorganize into new structures. Some elements concentrate in localized zones, where crystals begin to grow within the rock matrix. Garnet is one of the most familiar minerals produced in these metamorphic environments. In regions where schist formations have been exposed by erosion, garnet crystals sometimes weather out of the rock and accumulate in surrounding soils or streams. These crystals may appear dark red or brown in their rough state, often blending easily with ordinary gravel. Without understanding the geological environment that produced them, many of these stones would be dismissed as common pebbles. Another important environment for gemstone formation appears within igneous rock systems. When molten rock slowly cools beneath the surface, minerals crystallize at different stages depending on temperature and chemical composition. As the magma chamber evolves, certain elements remain concentrated in the last portions of the liquid melt. These mineral-rich remnants eventually solidify into coarse-grained rock known as pegmatite. Pegmatites are distinctive because they contain unusually large crystals. Elements that rarely concentrate elsewhere may appear within these formations, sometimes producing gemstones such as tourmaline, beryl, or topaz. In many parts of North America, pegmatite bodies cut through older rock formations like frozen channels of mineral-rich magma. Over millions of years, erosion gradually exposes these formations at the surface. Weathering then breaks apart the surrounding rock, releasing crystal fragments into nearby soils and waterways. Because of this process, streams flowing through pegmatite regions sometimes contain gemstones that originated far uphill from the river itself. The river becomes the transport system. Water moving downhill carries sediment from the surrounding landscape. As rocks break apart and move downstream, the river begins sorting the material according to density and size. This natural sorting process creates one of the most important gemstone indicators found in river systems: heavy mineral concentrations. Most rivers transport a mixture of sand, gravel, and organic debris. But certain sections of a river act like natural collection points where dense minerals settle and accumulate. When water velocity slows, lighter sediment continues downstream, while heavier particles remain behind. These deposits often appear as layers of dark sand mixed with coarse gravel. The dark color typically comes from minerals like magnetite, ilmenite, or other dense iron-bearing grains. Although these black sands may seem unremarkable, they signal that the river is capable of concentrating heavy materials. Because many gemstones are denser than ordinary rock fragments, they tend to behave in a similar way within flowing water. Over time, they may collect in the same locations where heavy mineral sands accumulate. For prospectors studying river environments, this connection becomes extremely useful. Instead of randomly searching along the entire river channel, attention focuses on areas where natural sorting concentrates dense material. River bends provide one of the most reliable locations. As water flows around a bend, the outer bank experiences stronger current, while the inner bank slows down. Sediment carried by the river begins settling along the inside curve where energy decreases. This process forms gravel bars, composed of mixed sediments ranging from sand to larger stones. Repeated flooding events gradually rearrange these deposits. Each flood lifts and redistributes the material before allowing it to settle again as water levels drop. Through this repeated sorting process, dense minerals slowly migrate toward the lower layers of the gravel bed. Gemstones transported from upstream sources can become trapped within these layers, sometimes resting directly above exposed bedrock, where movement becomes limited. Bedrock itself represents another important geological sign. When flowing water reaches solid rock beneath the sediment, natural cracks and depressions in the bedrock surface begin acting as traps. Dense materials carried by the river fall into these spaces, but cannot easily move further downstream. Over time, the cracks may accumulate heavy mineral grains, small gemstones, or metallic fragments, depending on the geology of the region. Prospectors often investigate exposed bedrock along river channels for this reason. The goal is not simply to examine the surface, but to observe how sediment interacts with the underlying rock structure. Small pockets within the bedrock may preserve concentrated material that remained undisturbed through multiple flooding cycles. Beyond river systems, another geological process sometimes influences gemstone distribution in northern regions. Glaciation. Large parts of Canada, northern United States, and parts of the United Kingdom were once covered by massive ice sheets during the last ice age. These glaciers moved slowly across the landscape, grinding rock beneath them and transporting enormous amounts of sediment. As glaciers advanced, they scraped fragments from mountains and bedrock formations, carrying the material sometimes hundreds of miles from its original source. When the ice eventually melted, the transported sediment was deposited across the landscape in irregular layers known as glacial till. Because this material originated from many different geological environments, glacial deposits occasionally contain minerals that do not match the local bedrock. In some cases, gemstones appear within these sediments, even though the original formation occurred far away. For modern collectors, this creates an unusual situation. A gemstone found in glacial gravel may not indicate a nearby source. Instead, it may represent a fragment carried by ancient ice movement thousands of years ago. Understanding glacial transport becomes essential when studying mineral distribution across northern landscapes. Geologists examine the direction of past ice flow to determine where transported material might have originated. By tracing these patterns backward, researchers sometimes locate the primary bedrock source of minerals discovered within glacial deposits. This type of geological reasoning illustrates an important principle in gemstone exploration. The stone itself is only part of the evidence. The surrounding landscape provides the larger context that explains how the mineral arrived there. Each fracture in the rock, each gravel deposit, and each mineral grain in the sediment contributes information about the processes that shaped the region over immense spans of time. Once those processes become visible, the search for gemstones stops being random. It becomes a process of reading geological signals left behind by the Earth itself. And those signals often appear long before the first gemstone is discovered.